right, we're going to look at kind of the second type of improper integral. These are a little bit harder to see because it doesn't look like there's anything wrong. There's no like infinity in the limits of integration. Okay, so there's a finite interval of integration, for example, down here, 0 to 1. But the problem is the interval spans an infinite discontinuity. And so that discontinuity can either happen at the endpoint or like somewhere in the middle. So notice here, the discontinuity is at x equals 0 because the graph of x to the negative 1/3, remember that's, right, is discontinuous at x equals 0. Okay, so there's a vertical asymptote there. So we have to deal with that in this type. Same thing here. Okay, there's a discontinuity here for x to the negative 3. So we have to deal with this type of improper integral before we do them. If you use a calculator, you can examine all these integrals here, and you'll notice that the top ones actually approach a value, whereas the bottom ones don't. So we'll address that in a minute. Let's just take a quick look at an exercise where we just describe whether each of these integrals is improper or proper. So this one's clearly improper because it has an infinite limit of integration, so it's definitely improper. Okay, those are obvious. This one here, that's harder to spot. It is improper because there's a discontinuity at x equals 2, and notice that in the interval 1 to 5, right, 2 is in there, it's right in the middle. So there's a discontinuity like interrupting this graph. So that would also be improper. We'll talk about how to deal with that. This is improper because there's a discontinuity at 2, which is right at the endpoint. Right, so this time the discontinuity is happening right at the end, at the beginning of the interval. Okay. Then there's this one. This one is not improper, and the reason is because even though there's a discontinuity at x equals 2, 2 is not in the interval 3 to 5. So this function behaves just like a regular continuous function on the interval 3 to 5. So this is totally legitimate, and there's nothing important. You can just use the fundamental theorem here, plug in 3 and 5. These other three, you'd have to do something different. Before I go on, let me just point out something. We've already learned from a previous video or earlier in the course that like if you're accumulating area under 1 over x this way, that's infinity. It turns out that this area is also infinity, okay, because there's symmetry for 1 over x. In other words, like the band of area going rightwards is the same as the band of area going upwards. So in both directions here, like this area here is also infinity for 1 over x. As soon as you start changing the exponent, that behavior shifts. So look, 1 over x is our blue and 1 over x squared is the green. We've seen that now this area actually sums to something. I think it's 2, I forget, but I'm pretty sure it's 2. Maybe it's 1. But it converges. But notice when you did that, like if I shifted the exponent to be 2, it made this part thicker. So now this is, that's too thick and it's infinity. Whereas if I kind of do the reverse game, if I make my p-value less than 1, again, remember the blue's 1 over x, this part gets thicker, right? This part here under the purple, that's infinity, but it gets thinner over here. Okay, so that actually converges to something. So this is all summarized here, and I already wrote this, or for my class, I had written this earlier. Okay, just take a note of that. The first type of improper integral with an infinite limit of integration like that, we can memorize this behavior. It'll be useful later when we're doing like exercises using comparisons. But so a to infinity of 1 over p will converge if p is bigger than 1, and it'll diverge if p is less than or equal to 1. Some textbooks put in this, but it actually, if p is a negative number, then it just makes sure it makes that expression inside become like a polynomial, and that will of course diverge. So like I kind of just leave it out to help make it simpler. But the behavior is reversed when you're integrating from 0 to a being any positive number. Okay, it's reversed. Okay, and this picture is supposed to try to get you to see that. When p gets greater than 1, it gets thick, right? When p is bigger than 1, it gets thick over here. It gets thick in the region between 0 and a. Whereas it gets thinner off to infinity, but if p is like a half, it's going to converge because it gets thinner over here by the y-axis. So this is just something to jot down and make sure you've got kind of squared away. It's a very useful behavior. I'm just going to do a few problems with you or for you, and then hopefully that'll get you enough to get going. So when it says verify our results, I already know from 0 to 1 because of what I just described here. This is going to converge because our p is less than 1. So let's see what it converges to. So how do we handle these? We replace the problem with a letter. Okay, let's just call that a now. Now on my interval 0 to 1, right, I'm replacing the 0 with an a, so I'll put it like here, and then I'm going to push it towards 0, and I'm coming from the positive side. So we write this integral as the limit as a goes to 0 from the positive side, and the integral is now a to 1. Let's write this as x to the negative 1/3. Okay, so we don't have to keep writing limit, limit, limit. Let's just analyze this first, and then remember that we're doing the limit as a goes to 0 from the right. So we use the fundamental theorem. We add a 1 to the exponent, so it's x to the 2/3, and then put a 3/2 there. And we're going from a to 1. So this becomes 3/2 times 1 to the 2/3 minus 3/2 times a to the 2/3. Okay, and now don't forget it's a limit. So what happens as a approaches 0? Okay, we're going to move a towards 0 from the right-hand side. Well, when a number that's getting smaller or approaching 0, 0 to the 2/3 is 0. Okay, so I mean, you can just substitute 0 in here. You're not dividing by 0, you're just evaluating. 0 to the 2/3 is 0. So this term vanishes, and we get 3/2 times 1 to the 2/3, which is 3/2. So we say it converges, this converges to 3/2. Okay. This one we expect to diverge because, again, p is bigger than or equal to 1. Okay, and so, again, we treat this the same way. We're going to write this as the limit as a goes to 0 from the positive side of a to 1. Call it x to the negative 3. Okay, and then we use the fundamental theorem to get an expression for this that doesn't have an integral involved. Add 1 to the exponent, you get negative 2, and then fix the constant, and then evaluate from a to 1. So this becomes negative 1/2, 1 to the negative 2, minus negative 1/2, a to the negative 2. Okay, now be careful here, right? So now a is not going to infinity, a is going to 0 from the positive side. So I usually like to make it really clear for myself, write a negative exponent comes down. Okay, as a goes to 0 from the positive side, what's happening is your denominator is getting really, really tiny, right? You're exponentiating a tiny fraction. So the denominator is getting tinier and tinier and tinier, but its reciprocal is getting bigger and bigger. So this whole expression is going to, well, I guess negative infinity if you can count this negative. But either way, that means, so this diverges. There's nothing else to evaluate. We noted that this right term goes to infinity. So we say this diverges. Okay, this integral diverges. Okay, and again, we expected that. Okay, because our p was bigger than or equal to 1. Let me just do this last one. So for a problem like this here, you could do a little u substitution. I think I'm just going to do it. You don't have to, though. I'm going to do it directly. Notice the problem here is this 27. There's a discontinuity at 27 because you'd be dividing by 0. Okay, and so what we're going to do is we're going to pick a letter, maybe like, I don't know. I'm going to use a because b's look like 6s sometimes. We're going to do the integral from 0 to a, and then we're going to push a towards 27 from the negative side. So this is the limit as a goes towards 27, coming from the negative side of the integral from 0 to a. And I'm going to write this as 27 minus x to the negative 1/3, so it helps me with the fundamental theorem part. Okay, so now again, antiderivative. Add 1 to the exponent, so 27 minus x to the 2/3. And then I need a 3/2 here. But then careful, I also need a negative, right? Because the chain rule would spit out a negative because of that. And so this should work. And now I'm going from 0 to a. And so I get this expression. Negative 3/2, 27 minus a to the 2/3, minus, that's the fundamental theorem, minus negative 3/2, 27 minus 0 to the 2/3. Okay, so now what? Everything hinges on what happens here. Again, a is going towards 27 from the negative side. You're really just, there's no funny business here, like that you're not dividing by a, there's no negative exponent, you're not dividing, there's no risk of dividing by 0. You can just plug 27 in, because as a goes to 27 from the left, then this whole inside goes to 0, right? So like this is approaching, so again, a is going to 27 from the negative side this time, but it's approaching this, okay, which is 0. So that leaves, so that vanishes, and that leaves behind 3/2, and then this is just 27 to the 2/3. So you're welcome to leave it like that if you want, but let's just note that that's, in this case, the cube root of 27 is 3, and then 3 squared is 9. So this is 3/2 times 9, which is 27/2, or 13.5, but that's fine. I'm not going to do this whole problem out. I just want to point out, this time the problem's right in the middle, right? Like in our interval 0 to 3, we've got a discontinuity at 1. These problems are real annoying. The way you handle them is you have to break this up at the discontinuity. So I'm just going to give you the setup, and we'll call it a day. This video is getting kind of long. Okay, so like you'd have to do this, and then you'd have to pick it up from 1 to 3. All right, and so then like you gotta get to kind of do 2 problems. So like you'd have to do this, right? You gotta replace the problem with, there's this 1. So a would approach 1 from the negative side, right? Because we're now on this section over here. Okay, and so then that would be the integral from 0 to a. And then like you'd have to, right? And then you'd have to use a different letter. It's probably best, you know, the integral from, the limit as b goes to 1 from the positive side of b to 3. Okay, and so then you just have to do them both. You should do one at a time, because if, like, let's say one of them was infinity, you don't have to do the other one, because you can't. Once you get infinity anywhere, you just say diverges. You can see these problems can kind of get kind of crazy. So just note the setup here. That's just technically what you need to do. And then you just got to do them both, because if they both converge, you add up the 2 numbers. Tricky. But anyways, that should give you a good foundation for this other type of improper integral. And good luck.